V at t represent the value of the car in dollars. Actually, let's say in thousands of dollars. After t, okay, now do we want to do months or years? This is what you should think about. This 18% is given each year, but they want to know the value of the vehicle in months. So I'm going to say it should be in years, but then when we go to find 30 months, we just have to represent that as in years. So how much is 30 months in years? So V at t then would equals the initial value, which is 24, since we said in thousands, times, now the b value, remember, is 1 minus the rate, okay, because it's decay. So 1 minus 0.18 to the power t. So V at t is 24 times 0.82 to the power t, okay? So it's decaying by 18% a year. You can also think about it that the next year it's worth 82% of what it used to be worth. So t is 30 months, which is equal to 2.5 years, right? Because 24 months is 2 years, sorry, and then there's 6 more months after that, and that's another half year. So we just solve V at 2.5, you plug that in, and you get 14.6. So you say, therefore, the value is $14,600 after 30 months. Okay, our next example, we've done a half-life example, we've done a growth example, and a decay example. The next one is a doubling time example of another very common application of exponential growth. Okay, so a bacterial colony with an initial population of 300, doubles every day. So we want to model this exponential growth with an equation. So we'll say let P at D represent the population at day D, okay? So our population starts at 300, okay, and is doubled. So remember, that means B equals 2. Okay, sometimes people do B equals 3 because they think they need to do 1 plus 2, that the rate is 2. But that's not the case. Doubling means it's increasing by 100%. Okay, so 1 plus 1. Or you can just think of, you need it to be 2 because it's double time. And that's to the power of D. So again, if you need to make sense of this, this is 1 plus 1.00, since it's 100% growth. That's what doubling means, 100% growth. So the Petri dish in which the colony lives can hold up to 4 million bacteria. When will the bacteria stop growing? So this means you need to set your 300 bracket 2 to the power D equal to 4 million. Okay? So we can divide the 300, but we can't do anything with the 2. So we take 4 million and divide by 300. And we're left with 2 to the D equals, sorry a second. Well, it's 4 million over 300. So it's 13,333.3 repeating, okay? Just gonna check my math here. Yeah, 13,333.3 repeating. So now we have to do our little estimation thing, or we have to do, our estimation thing on the calculator. So 2 to the power D. So what do you think you want to start with? 2 to the power what? how many times do you have to double to get to 13,000? It's not as much as you might think. Let's try to the power of 50. Okay, I get some humongous number. It's in scientific notation on my calculator. That's obviously way too big. So let's say I'm going to have that 2 to the power 25. 2 to the power 25 still gives me some humongous number. That's way too high. So now I'm going to try 2 to the power 15. 32,000. So think about it, 32,768. That's about less than half of that. So I'm getting close, okay? Because 2 to the power 14 then, okay, 2 to the power 14 equals 16,384. And then 2 to the power 13 is way too low. It's 8,192. So it's somewhere in between those. So D represents the number of days. So when will the bacteria stop growing? Well, if we want to say to the closest day, we can say late in day 13, the bacteria will stop growing. Okay, because if we say after 14 days, that's not true because it's gone up way too high after 14 days. So it's somewhere between the 13th and the 14th day. And if you say something like late in day 13, that shows me critical thinking that it's closer to day 14 than day 13, but it's not quite at day 14 yet. All right. Okay, the last question, I'll be honest, is kind of abstract, and you won't really be getting much like it in your homework. It's just kind of an actual real-world problem, and it shows you how hard mathematical modeling actually is. And often, real-life situations don't fit our pretty little math perfect world. So, in the year 2002, a single girl was born with the name Nevaeh. Pretty name, right? 2 years later, there were 18 girls, including the first one with that name. So, let's make a little chart here. So, year and number of girls with that name. Okay, so we have 2002. There's one girl with that name. Then after 1 year, we don't know, it doesn't tell us. After 2 years, there are 18 girls with that name. And in 2005, so that would be year 3 then. Oh, sorry, this is 2003, 2004, and 2005. There's 70 girls. So is this an example of exponential growth? What would the growth rate be? And create a possible equation to model the growth in popularity. Okay? So the limitations are, you'll see this is not a constant rate of growth. We also have a limitation because we don't have any data for 2003, so there is a big gap there. So those are 2 limitations right off the bat. If we go between 18 and 70%, we can find the percent increase there. So you do 70 minus 18 divided by 18 gives you 2.89, which means 289%. All right, so that's interesting. So if we apply it to the first, if you look there, you get 289%. So remember that. So that would mean our B value then would be 3.89. But if you try that, it doesn't really work that great because it doesn't really fit the data completely. If you start throwing in these years, okay, so you let this be like year 0, year 1, year 2, and year 3, and you try these, like if you try 3.89 to the power 2, you get 15, whereas if you do 3.89 to the power 3, you get 58. So I didn't get anywhere near 70 kids. So this rate is really too low because it doesn't really represent what's going on here. Okay, because I'm just going between years 2 and 3, not from the beginning. So we want to try a b of 4, so that would be 300% growth. Okay, so slightly higher than what it was between those two. So if I try that, if I try 4 to the t, that ends up being too low. Okay, if I try 4.2, so 320% to the power t, that ends up being too high. So you can see here that there are limitations to using exponential growth in the real world. So the best way to actually do this would be to get out your Excel and your Microsoft Excel on your computer and actually plot these points with 0, 2, and 3 on the y-axis and 1, 18, and 70 on the y-axis. And do something called exponential regression, or try to do a line of best fit. That would be exponential. Okay, there's also a way on your calculator, your graphing calculator, that you're able to do exponential regression as well. So I'll start with that next time or in class and show you how that's done. But the whole point of this problem is just to show you that there are limitations in the real world, and not everything is nice and beautiful and perfect as we like to think it is in math class. But in high school, it's just most important that you understand the basics and understand what happens when there is perfect data, so that when you get imperfect data, you're able to understand how to best match a function to the data that you're given. So that might have gone a little bit confusing and theoretical at the end. So if this example was totally over your head, don't worry about it, to be honest. But examples 1 through 4 are very, very important. So I hope you learned a lot about applying exponential functions and that you had a good time doing it. Thanks for watching, and I hope you learned lots.